In this video, we're going to take a look at approximating a binomial distribution. If we have a random variable that follows a binomial distribution with parameters n and p, it can be quite challenging to find probabilities for our random variable when n is large. And the reason for this is because the binomial tables within the formula book only go up to n equals 50. However, under certain conditions, we can use a normal distribution to approximate a binomial distribution. So the question here is then, what are the two conditions? So my two conditions here then, well, for the first condition, we require that n is large. We say n is large. And here for n being large, we define n as being large when n is greater than 50. And then for the second condition here, we require the probability p to be close to 0.5. We say p is close to 0.5. So if these two conditions hold here, we say if these conditions hold, then we can take a random variable, let's say x, which follows a binomial distribution with parameters of n and p. And this can be approximated then by y, which follows a normal distribution with parameters of mu and sigma squared. And in this case then, mu here, that is equal to n times by p. And then for sigma here, the standard deviation, that is equal to the square root of np times 1 minus p there. Now, before we take a look here at any kind of practice questions, you should be aware that the binomial distribution is a discrete distribution and the normal distribution is a continuous distribution. So what this means then is we have to apply a continuity correction when we're using the approximation. And I think this is often where students struggle now with the approximation here. So for a continuity correction, well, to begin with, let me just kind of define a random variable here. So let's say we've got x, which follows a binomial distribution with parameters of 16 and 0.5. So if I was to use the approximation here, well, for a start, it wouldn't be very good because n clearly isn't large. Okay, so 16 is clearly not greater than 50. But I've just picked these numbers for convenience. Okay, so don't worry too much about the numbers here. All we're concerned about is the continuity correction. So if I was to find the approximation here, well, we'd have y. Y is normally distributed. So for mu then, that would be n times by p, so 16 times 0.5. That would be equal to 8. So mu equals 8. And then for the variance here, well, let's start by finding the standard deviation. That's equal to the square root of np, which is 8 there. Then we times it by 1 minus p, so that's 1 minus a half. We times it by 0.5. So 8 times a half is 4. So what I've got here is the square root of 4, which is equal to 2. So the variance then is 2 squared. Okay. So this is my approximation here then. Now, let's say we want to find a probability then. So let's say we want to find the probability. Our random variable x here is greater than or equal to 10. Okay. Now, I think the easiest way to work with a continuity correction is to just consider we're either going to add 0.5 or subtract 0.5 from this value here. So you need to determine then whether we add 0.5 or subtract 0.5. And the way to understand that is to consider this inequality here. So for our approximation then, this would be the probability that y. Now in this case here, we're looking at x being greater than or equal to 10. So we need to include the 10 here. So x is greater than or equal to 10. So it could also be 10 as well. So in that case then, what I need to do here is subtract 0.5 from 10. Because in that case then we would include the 10 here as well. So we say y is greater than 9.5. So let me just redo that 9. So it's neat here. So 9.5 there. Okay. So in that case then, what about if this is a strict inequality here? So what about if we have the probability of x being greater than 10? Well, this time now, we don't want to include the 10. So in this case, we add 0.5 now to 10. In this case, we get the probability that y is greater than 10.5. Okay, because this time now, we don't want to include the 10, so we add 0.5 there. So now let's consider if we are less than or equal to 10. So if we have the probability that x is less than or equal to 10, what would this be here? We'll just consider this for a moment. So here we're looking for x being less than or equal to 10. So we want to include the 10 here. So now I need to add 0.5. Okay, because we want to include the 10 then. So in that case, we're looking for the probability that y is less than 10.5. Okay. Think about this on a number line then. So I want to include the 10. I need to be slightly bigger so that we include it. So what about now if this inequality here is strict? We're now looking at the probability that x is less than 10. Well, for our approximation then, this would be the probability that y. Well, here we don't want to include the 10, so we need to be smaller than 10. So in that case, we're now going to subtract 0.5 off. So y here would be less than 9.5. Okay. And then finally, all that's left to consider here is what about if we have an exact probability? So what about if we have the probability that x is equal to 5? Okay. So for the approximation here then, well, you can see for the past few examples here for these continuity corrections, we've either added 0.5 or we've subtracted 0.5. Now in the case here of an exact probability, we do both. So y now is going to lie between 4.5, so we subtract 0.5 off. So it's going to be between 4.5. And then you might have guessed what the upper value here will be. We're now going to add 0.5 to this value here of 5. We get 5.5 there. And there we have it. So that would be our continuity correction there. And it's important that you always apply a continuity correction here. There isn't, a situation where we might not apply it. If we approximate, we do apply a continuity correction. Okay. But there we have it. So that's everything that we need there then for our introduction here to approximating a binomial distribution. What we're going to do now is take a look at a couple of practice questions for approximating a binomial distribution. Starting off with question 1 then, where it says for the given random variables x that follow a binomial distribution, find the normal approximation to x in this form here, stating the values of mu and sigma. So we start then with part A. So for part A then we have x, which is binomially distributed. X is binomially distributed. And then for the parameters here, we have n equals 75. And P, the probability, is 0.54. Okay. So we can find the normal approximation here because n is large, so n is greater than 50, and P is close to 0.5. So that's fine. So when we find the normal approximation here, that would be in this form, where mu is equal to n times by p. So let's just note that here. So mu is equal to np. And then for the standard deviation here, sigma, that is equal to the square root. We have the square root of np times by 1 minus p there. Okay. So we start by finding the mean here. So that's n, which is 75. Times that by p here, which is 0.54. So if you evaluate this here, what you should get then is 40.5. We get 40.5 there for mu. And then for sigma here, what am I going to get? Well, this would be the square root. So it's going to be MP, which is 40.5, because this is just simply MP. So you get 40.5 there. And then we times this here by 1 minus P, where for part A then, P is 0.54. So 1 minus 0.54. Again, you need to evaluate this here. So now if I round this answer here to 3 significant figures, what you should get then is 4.32. So 4.32 there. Okay. So we found the value of mu, we found the value of sigma. So now if we just write it in this form here as required, what we get then is y, which is normally distributed. So mu is 40.5. 40.5 there. And then for the variance, that would be 4.32 squared. Okay. And there we have it. So that's the solution to part A. So now let's move on to part B. So for part B then, x is binomially distributed, where n is 350 and p is 0.48. Okay. So again, we can apply a approximation here, or an approximation, because n is large, greater than 50, and p is close to 0.5. So again, we need to start by finding mu and sigma. So mu here, that's going to be equal to 350 times by p here, the probability, so that's 0.48. If you just evaluate this here, what you should get then for 350 times 0.48 is 168 there. Okay, so that's mu. We now need sigma. So sigma here again, we just use this formula. This would be the square root. It's going to be MP, which is 168 there. Then we times that by 1 minus P, so that's 1 minus 0.48. All you need to do here is evaluate this, and if you do this correctly, then what you should find for sigma here, again, to 3 significant figures, is 9.35. You get 9.35 there. And again, if we just give it in this form here as required, what we get then is that y is normally distributed. So mu then is 168. And the variance is 9.35 squared. Okay. And there we have it. So that's the solution to part B. And then finally, we've got part C here. So what I'll do is I'll just do that next to part B here. Let me just split this off a little bit here. So for part C then, what I've got is x is binomially distributed, where n equals 300 and p equals 0.52. So again, I need to start by finding mu here. So nice and straightforward then. Mu is equal to n, which is 300, times by p, which is 0.52. So again, just evaluate this here. 300 times 0.52. What you should get then is 156. You get 156 there for mu. And then for sigma here, this is equal then to the square root of MP times 1 minus P. That's going to be the square root of 156 times by 1 minus P, where P is 0.52. Okay. And again, just evaluate this here. Again, I'm going to give my answer to 3 significant figures. So what I get then is 8.65. 8.65 there. So finally then, all I need to do is give the answer in this form here. We didn't mention it for part C, but again, I can find the normal approximation here because n is large and p is close to 0.5. So y in that case then is normally distributed, So my parameters here are 156. And then for the variance, that would be 8.65 squared. Okay. And there we have it. So that's the solution to part C, and that gives the solution there to question 1. So if we just take a look then at one more question here, we've got the random variable x, which is binomially distributed with parameters of 200 and 0.52. Let's just start by denoting this random variable x here. So x follows a binomial distribution with parameters of 200 and 0.52. So the question says use a suitable approximation to estimate, and then we're given these 3 probabilities here. So because we start with a binomial distribution, and we're going to use a suitable approximation here, well, because n is large, so n is greater than 50, and p is close to 0.5, that would suggest then that we're going to use a normal distribution to approximate this binomial random variable here. Okay, approximate its binomial distribution. So in that case then, we can approximate this as y following a normal distribution with parameters of mu and sigma squared, where mu is equal to np, and then sigma here, that's given us the square root of np times 1 minus p. So in that case then we need to start by finding mu here. So n times by p, so that's n here from the original random variable x, so that's 200 times by p, which is 0.52. So 200 times 0.52, what that gives me then is 104. And now if we evaluate sigma here, this is the square root. So it's np, so that's 104. And then times that by 1 minus p, where p is 0.52. Like so. So now if we just evaluate this here then, don't forget the square root as well. If I round this to 3 significant figures, what I get then is 7.07. Okay. What we've got then is y, which follows a normal distribution. So mu is 104. And the variance then is 7.07 squared. Like so. So now we start by finding this probability here. So for part A then, we want to find the probability that x is greater than 105. Okay. So obviously we can't find this probability here, okay, using the tables from the formula book. So we're going to use our approximation then. So we've got our approximation here. So this will be approximately then the probability. Now, because we've gone from a discrete distribution, remember the binomial distribution is a discrete distribution, to the normal distribution, which is a continuous distribution, what we need to do now is apply a continuity correction. And I think often students overcomplicate this. It's not actually too challenging when you think about it, because all I'm going to do here is consider now whether we want to include the 105 or exclude that 105. Okay. So because we don't want to include the 105 here, okay, we're strictly greater than 105. We need to be 0.5 bigger. Remember, we work in plus or minus 0.5. So we're either going to add 0.5 or subtract 0.5. So here, we don't want to include the 105. Okay, we're strictly greater than 105. So in that case then, for my approximation here, this is the probability that y is greater than 105.5. Okay, so we just add 0.5 there. So here then, to find this probability, we're going to now use our calculator here. So I go into stats mode, but then press distribution. So distribution. When I press that, obviously I get a number of different distributions here, but the one that we want is the normal distribution. So I press norm there. So that's for the normal distribution. And then when I press norm here for the normal distribution, I get 3 options. I've got NPD, NCD, or inverse N. And the one that we want here is NCD. So NCD there. Now I get asked for a number of different things here. So I get asked for the lower, We get asked for the lower, the upper. We get asked for sigma. We also get asked for mu. Okay. So we'll ignore the lower and upper for now. We'll come back to those in a moment. But obviously, sigma and mu, nice and straightforward. That's just these parameters here. Okay, so for mu, that's 104. Obviously, just be careful you get this the right way around. Sigma comes first and then mu here when you input this into your calculator. And then for sigma here, that would be 7.07. Now for the lower and upper, remember this is determined by the probability that we're looking to find. I want the probability that y is greater than 105.5. So because we're looking for y being greater than 105.5, that means I need to input the lower value here as this value. So lower is 105.5. And then for the upper value here, I just input an arbitrarily large value. I usually just put a load of 9s here. Any arbitrarily large value, like I said, would be absolutely fine. Okay. So if you input everything in correctly here, what you find then for the probability here is this is equal to 0.416 there, to 3 significant figures. Okay. And there we have it. So that's the solution to part A. So that was the continuity correction there. And that is our probability. So for part B then, well, we've done most of the hard work here. We've got the approximation. All I need to do now is apply the continuity correction and then find the probability using our calculator. So for the probability that x, or random variable x, is less than or equal to 96. So x is less than or equal to 96 here. Well, again, we now need to apply the continuity correction here. So this will be approximately, it will be the probability that y. And again, let's just consider now what we actually want here. We want x being less than or equal to 96. So here, we do want to include the 96. We want to include that. So if I subtract 0.5 off here, that would be the probability that y is less than 95.5. And in that case, then we would be excluding the 96, but we want to include it. So we're not going to subtract 0.5 here. We're actually going to add 0.5. Okay, so y must be less than, that would be 96.5 there. Okay. So all I need to do now is use my calculator again, just following the same pattern here. So distribution, normal, NCD. And again, I need to input the correct values here for the lower, upper, sigma, and mu. So obviously, sigma and mu won't change. We're using the same approximation here. So all I need then is the lower and upper. So lower and upper here. So for part B then, well, now the probability here is y being less than, so less than 96.5. So now we input this value here into the upper. Okay, so that's going to be 96.5. So 96.5 there. Okay. For the lower then, we now pick an arbitrarily small value. So here I just put a load of, I just put minus 99999, like so. That's fine. Obviously, sigma and mu, they'll be the exact same then as they were in part A. So if you're using your calculator again, you won't need to change those, so that's fine. So again, let me just quickly do that on my calculator here. Minus 9999 and 96.5. And what I get then, to 3 significant figures here, is I get 0.1 over there. Okay, so that's our solution to part B. That was the solution to part A. And then finally for part C here. So let's do that over on the right hand side here. Just split the screen off a little bit here. So for part C then, we're looking for the probability that x is equal to 102. Probability that x is equal to 102 then. So now, again, we need to apply a continuity correction here. So in this case here, remember, when we're looking for an exact value like this here, we now need to add and subtract 0.5. So what I do then is I subtract 0.5 off, and I also add 0.5. So what I do then for my approximation here, this would be the probability that y is going to be between 101.5. So if I subtract 0.5, I get 101.5. 101.5. And then for the upper bound here, that would be 102.5. So adding 0.5 there. We get 102.5, like so. So now all I need to do here is go into my calculator again and use the lower, upper, and then sigma and mu here to find this probability. So again, it's distribution, normal, NCD again. We've got lower, upper, and obviously sigma and mu again won't change, so they're the same. So just leave those as they are. So for the lower and upper here, it's actually nice and straightforward. So my lower value here is the lower bound of this probability. So that's going to be 101.5. And then for the upper bound here, that would be 102.5. Okay, nice and straightforward. Sigma, well, that's just 7.07 again. Mu is 104, so don't change those. So if I quickly put that in as well, 101.5 and 102.5. What I get then, my probability here is 0.0. I get 0.0542 there. So 0.0542. And that's two free significant figures there. Okay. And there we have it. So like you can see, applying the continuity corrections isn't too challenging. We just need to kind of think about that logically, whether we include that value. Like you can see here, we include 96, so we need to add 0.5, or whether we're going to exclude this value like you can see here in part A. So we now need to add 0.5 there to exclude 105. So hopefully you found this video helpful. Like you can see then, that is the solution to the very last question. And that brings the end of this video on approximating a binomial distribution.